Good morning, Honors Chem students. Mr. Lambert here, April 6th, 2020. I'm trying something a little bit different. I have my gaming headphones on because some of the other videos I've posted for my other classes, including yours, the sound gets a little choppy based on where my head is. So I wanted you to be able to see my board. Let's get right to it. I'm going to post a couple videos today. One dealing with something called empirical formulas, and the other dealing with molecular formulas and how to calculate these. It's going to help you finish up your Chapter 7 work. I'll also be pushing out a worksheet with just a few problems today on empirical formulas, and those will be due tomorrow. I'm going to hold off on the poggles just for a little bit to change it up, so to not bore you. As you can see on the board, an empirical formula, the definition straight from the textbook, the lowest whole number ratio, whole number, that's important, of atoms in a compound. The empirical formula, and I added this, by the way, this second sentence. The empirical formula is not always the actual molecular formula of the compound. Basically, it's a whole number ratio, but it's simplified. It's not necessarily what the actual structure of the chemical is. But empirical formulas are important because they tell us the simplest, smallest whole number ratio in a particular compound. Below, I have a few examples, 4 different chemicals. Here are the names. Let's look at benzene, the first chemical that I have here. Benzene is a chemical that's actually in the shape of a hexagon ring, hexagonal. It's got 6 carbon atoms bonded in a ring, but attached to that ring are 6 additional hydrogen atoms. So the actual molecular formula is C6H6. The question is, can that particular ratio of a 6 to 6 carbon to hydrogen, can that be simplified? Of course it can. So the empirical formula, if you divide everything here by 6, you can get the lowest whole number ratio of CH. Even though CH is not actual benzene, it does tell us the ratio. Look at the next one. Glucose. The actual molecular formula of glucose, the sugar that plants are making, the sugar that we as humans and animals are breaking down for energy, the actual molecular formula is C6H12O6. Look at those subscripts of carbon to hydrogen to oxygen. Can they be simplified? Yes. What I've done over here is I've simplified them all by the least common multiple, least common denominator, and that's 6. So that's going to break down into an empirical formula of CH2O, twice as many hydrogens as there are carbons and oxygens. Real quick, here's another one, covalent compound. The name, I figured I'd throw this on here because we did covalent compounds not too long ago. Tetraphosphorus decoxide, P4O10. That's the actual molecular formula. Can it be simplified? Yep. P2O5 is the empirical. Everything can be divided by 2 to get the simplest whole number ratio. For every 2 phosphorus atoms, there are 5 oxygen. Check this one out, water. We all know water. Its molecular formula, the actual chemical, is written as H2O. Can that be simplified? No, because for every 2 hydrogens, there's simply 1 oxygen in the molecular formula. So in this particular case, the empirical formula and the molecular formula are the same. Now I'm going to give you an example problem on how to calculate a compound's empirical formula. Okay, here's a pretty classic empirical formula calculation problem. Notice this is from page 208 in your textbook, sample problem 7.8. It's a problem that only deals with 2 elements, but they're part of a compound, and it's our job to figure out what the lowest whole number ratio is. The problem states, experimental analysis shows a compound to contain 6.87 grams of iron, there's our first element, and 13.1 grams of chlorine, element number 2. It wants to know what the empirical formula is. Well, hopefully, by now we know that you cannot compare the masses of 2 different elements directly because they don't have the same molar mass. They don't weigh the same. So what we need to do And this should be, unfortunately, even though we haven't been at school, if you've looked at the other videos, this should be review. We need to get the grams of each of these elements into moles, and then we can compare the moles of one chemical to the moles of another, and we'll figure out the whole number ratio. So let me set it up real quick. The first element is iron. We have 6.87. It's hard for me to write like this, but 6.87 grams of Fe. We're going to get grams of iron into moles of iron. So we're going to put grams over 1. We're going to do a little dimensional analysis here. Grams of iron is going to come down. We're going to cancel out that unit, and we're going to convert grams of iron into moles of iron, moles of Fe. Let me extend that. Hopefully everyone can see it. This is where we're going from grams to moles. Whenever we need to do that, we need to use the molar mass from the periodic table. It tells us for every 1 mole of iron, there are 55.85 grams of iron. That would cancel out, that would cancel out, and we don't need to go any further. We can simply look at how many moles of iron are in front of us. I'm going to pause it so I can get the book and make sure we all have the correct answer here. On page 208 in the book, it tells us we have, in terms of moles of iron, 0.123 moles of Fe. We can't do anything else right now. We have to compare the moles of iron to the other element in the compound, so we're done for this section. It's simply grams into moles. Next, we're going to do chlorine. Let's start in grams, use the molar mass to get it into moles, and get a number of moles of chlorine. So we have 13.1 grams of Cl. We'll put that over 1. We will cancel out grams of Cl, get it into moles of Cl. Again, we're using molar mass. For every 1 mole of Cl, the periodic table tells us there are 35.45. Once again, it's a division problem. Grams of Cl cancels out, and we have in front of us 0.370 moles of Cl. This should be review. We should all know how to do this. We simply went from grams to moles. Here's the only thing that's different with empirical formulas. Don't forget we want the lowest whole number ratio. So now that we have 2 amounts in moles in front of us, the trick is you need to look and see which one is the smallest number, in this case, of these 2 elements. You're always going to divide by the smallest number and set that particular number to 1. We're going to try to get the lowest whole number ratio. Check this out. If I realize that I have 0.123 moles of Fe, which is smaller than this number, I'm going to divide both numbers by the smallest one, the smaller of the 2 in this case. So I'm going to divide by 0.123 moles of Fe. And I'm also going to do the same thing here. Divide by 0.123 moles, in this case of Fe. I'm running out of room, but any number divided by itself, we are going to set this right here, the smaller of the 2, to 1. What I like to do is I like to put a 1 and circle it. I know that my ratio for Fe right now is 1. The question is, what happens when we divide 0.370 divided by this? The textbook tells us that if you calculate this, you're going to end up with 3.01 moles of Cl for every 1 mole of Fe. Now, because not all these numbers are completely accurate to lots of sig figs, there's going to be rounding involved. Hopefully you can understand that 3.01, what whole number is that really close to? It's the whole number is close to 3. So basically what we're saying is, I'm going to put a 3 here and circle it. What we're saying here is for every 1 mole of Fe, we have 3 moles of Cl. And from that, we can come up with an empirical formula. Based on how they give us the information, we can simply say it's a 1-to-3 ratio. I'm going to write it right here. Our final answer is an actual formula, an empirical formula, FeCl3. Okay, one more example to help you out. The last example I gave you, there were a certain number of grams of two elements, and you simply had to go from grams to moles, divide by the smaller amount of moles to get a ratio. Sometimes you're going to see elements listed as a percentage of a compound and not grams. So this is page 212, problem 7.45D. I did an odd number so you could see the answer, which is at the end of the section. This particular compound has 18.8% by mass lithium, 16.3% carbon, and 64.9% oxygen. I chose one that had 3 elements this time. Well, don't freak out over the fact that these are percentages and not grams like the last part of the video. If you add all of these up, the problems that you're going to get from me and hopefully from future teachers or professors, these percentages will add up to 100%. So there's no crazy math that you have to do. Simply assume, because all of these numbers add up to 100%, assume that you have 100 grams of the compound, a nice round even number, 100. So instead of 18.8% lithium, you're going to ignore the percent and you're going to say you have 18.8 grams of lithium. Same for the other two. I'm going to set up the 3 solutions so we can find the empirical formula. Okay, last part quickly. I have set up grams of lithium, carbon, and oxygen based on the percentages. Notice the numbers are the same. I'm dividing by the grams of each, but dividing by the molar mass of each chemical to get them into moles. I've provided that for you all right here. So you have moles of lithium, carbon, and oxygen. First, take a look. Which one is the smallest of the 3? Let's set ourselves up with a ratio. The smallest of the 3 numbers is right here, 1.36. I'm going to divide everything by 1.36. When I say everything, each of these 3. Let's do this one first because it's carbon, and we know it's going to come out to 1. So if I divide this by 1.36, I'm going to say that we're going to set that whole number to 1. Carbon for right now is 1. Some of you that are math whizzes, some of you can probably eyeball this without even doing the division. 1.36 versus 2.71. That's pretty darn close to 2. It's not going to come out to be a perfect whole number because of rounding. If I do 2.71 divided by the smaller number 1.36, I get, I don't know if you can see that, 1.99. I think we can go ahead and call that 2. So right now we have 2 lithiums for every 1 carbon. Let's see what our oxygen ratio is going to be. 4.06 divided by 1.36. Oops, sorry, I should have done this. We're going to divide it by 1.36. Everything's divided by the smallest number. So let's see if you can see it here. 4.06 divided by 1.36, and we get for oxygen 2.98, 2.99, if you're thinking about rounding to 3 sig figs. 2.99, I think we can go ahead and call that 3. So here you have it, folks. For every 2 lithiums, you have 1 carbon and 3 oxygens. You can write the empirical formula in the order that the elements were given to you. Right up here, and I'm going to circle it. Li2, whoops, no comma. Li2, C1, so no subscript. Li2, CO3. And that is the empirical formula. Let me make that 3 better. That's an empirical formula from percentages and grams.